Pretty interesting, let's say. Um, that was one that, oh, I mean, if you saw my, if you could, if you look at my videos, you'll see that I spent like an hour and a half on it. Um, and it really was like the last 15 minutes where I was really properly working on the problem. The rest of that time was just sitting there kind of trying to figure it out. But dang, that was such a cool problem. Thanks to one of my viewers, Blue Ghost, for pointing me in the right direction and getting it. We were so close getting to that. We almost managed to get an answer out of Wolfram Alpha instead of writing our own program to solve it, but I didn't have the syntax down to coax Wolfram Alpha to give me an answer. And it turned out that all you had to do was type in all the separate equations into Wolfram Alpha, and it was powerful enough somehow to work out the answer for us. But we only discovered that after I had implemented it. And I don't want to spoil it, but yeah, it was a very mathematically based challenge. Honestly, I really enjoyed doing that challenge. I enjoy scratching my head over like a puzzle that on the surface seems quite straightforward, but when the actual implementation is tricky, yeah, like it was so hard to decide whether I liked it or not, right? Yeah, because like it was so cool. I love sitting down and trying to figure out a solution, but like it was one that I knew I wouldn't be able to come up with by myself, right? Like, but then like having just enough help, knowing what mathematical theory we needed to use to do it, and then reading up on it, learning it, and then turning it into code and making it like it was really satisfying in the end, being able to solve it. And yeah, so I guess there were a couple of learnings from that, eh? Like Wolfram Alpha is really powerful. Don't help it too much, and it might just spit out the answer that you want. Yeah, because Blue Ghost, my viewer, he typed it in a different way. It was probably even more abstract than the way I typed it in, right? Because I typed it in with like 7 equations with 7 variables, and he typed it in, or she, with 1 variable, and it gave like the answer straight away. So hopefully today it will be a bit of a different flavor, not one that relies on, I think we were saying yesterday, a PhD in maths to solve. Yeah, cool, got it. Blue Ghost, yeah, and yeah, it was strange, right? How over integers power was irrelevant, because I guess yeah. So if you haven't watched yesterday's video, I typed in, because we needed integer values, right? So I added, because I knew you could give Wolfram Alpha a domain to solve over, right? To say like only give me integers, or only give me between these values or whatever. And so I thought, I was like, oh, if I don't do this, it's gonna give me like real solutions, which wasn't what we needed for the challenge. So I typed solve my equation over integers, and it turned out that no, Wolfram Alpha is just smart enough to not need that. I don't know, insert joke here about Skynet or something like that. Anyway, we have 10 seconds to go, so I am super excited. Let's see what today's challenge is. Here we go. I'm gonna open my puzzle input as well. So we're now on the ferry going towards the seaport, and they need help with docking, it seems like. Yes, docking the ferry. So after a brief inspection, we see that the seaport's computer system uses a strange bit mask system in its initialization program. So we don't have the decoder chip the hardware chip ready, but we can emulate it in software. Cool. That's what we'd like to do. The initialization program can either update the bit mask or write a value to memory. Ooh, interesting. Values and memory addresses are both 36-bit unsigned integers. Luckily with JavaScript we don't have to worry about that. I think everything's a double is what we usually say. But yeah, well, we'll see what happens. For example, ignoring bit masks for a moment, a line like mem811 would write the value 11 to memory address 8. The bit mask is always represented as a string of 36 bits, written with the most significant bit representing 2 to the 35, yep, on the left and least significant on the right. The current bit mask is applied to value. So that's as you would expect. The current bit mask is applied to values immediately before they are written to memory. A 0, 1 overwrites the corresponding value, while an X leaves the bit in the value unchanged. For example, consider this. Okay, that seems pretty straightforward, right? So it's going to overwrite. So like the first line is going to write a 1 instead of a 3, right? I believe. Yeah. The program then attempts to write the value 11 to memory address 8, but it gets overwritten. Ah, right, and the other one becomes a 1. Yep. Cool, so because of the mask, that is written instead. Then it tries to write 101, which is 5, to address 7, and it writes that instead. Right. Wait, what? Oh, it's decimal 101. Oh, these are decimals, not binaries. Okay, cool. Almost messed that one up. 64 is written instead. To initialize your fairy stocking program, you need to sum all the values left in memory after the initializing program. The entire 36-bit address space begins to initialize to 0 at every address. So, yep. In the above example, only 2 values in memory are not 0. 101 at address 7 and 64 at address 8, producing a sum 165. What is the sum? Okay, so that seems pretty straightforward, right? I wonder if, like, this probably makes more sense like this. We actually just paste our input straight into our program, and we'll just like do a little bit of massaging on this data. So function setMask string, and we'll call it function write mem address value. So we just do something like this, and I have a couple of global variables sitting around. Let ones mask. I think we'll need to split the mask into ones and zeros. Ones mask equals 0. Let zeros mask equals 0. I think these need to be different numbers later on. Do that. Then here. Yep. So we just need to do a little bit of search and replace here. So mask equals stuff. We need to replace that with set mask brackets the input as a string, and replace all of that. Cool. And with the write mem, okay, so we need a memory, right? So mem that equals that. We want to replace that with write mem address value. Yeah, so this is just finding and replacing our input. And I didn't put a semicolon at the end. Cool. And then here we need a sum thing, right? To sum it, that's quite straightforward. Let sum equals 0 for const key of in mem, so that gets us all the keys in mem. Sum plus equals key mem key, and then we print sum. We'll also print mem just in case. So right off the bat, we'll just check that this works. Oops. One's mask was unexpected open bracket. Nope, all good. Cool. So let's see how we set mask. Set mask, we want to get all the ones and zeros out of this. Yeah, I could probably I could probably do something like that. That works too. I'll just leave it the way it is because for my brain this seems to work nicer. Blue Ghost mentioned that I could do object.values, and then some kind of and then do a reduce over that. Yeah, that would be totally fine as well. So I think, so what do we need? How do we overwrite values with 1? We overwrite values with 1 by doing an OR on the mask, right? Yeah, so 0 mask, 1 mask, 1's mask, just to make them the same length. So what I can do is I can go string.replace, and I need to figure out how string replace works in JavaScript because that's what I always have to do. I think this is a thing, right? ABC 0 with, let's go with X just to see what this does. I need a G here, I think. Yeah. Cool. So with string.replace here, I want a 1's mask. 1's mask should be, I want to pull out all the 1's and get rid of all the 0's and X's dot okay, it's got replace all. So with replace all, do I just do like this instead? Apparently my Node doesn't have it. I have an older version of Node, maybe? Version 13? Yeah, I want to replace them all with zeros. So I want to replace all the X's with zeros, I guess. In fact, then I can just do this, right? Okay, so that gives me, so I'm just going to return here, just to see what happens here. Now this time I do need parse it, because I can parse it as a binary number. Can I print that as a binary number, or can I not? We'll just do it by hand. See what happens. Let's see. 0, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 0, 0, 0, 0, 1, 0, 1, 1, 0, 1, 0, 0, 0, 0, 0, 1, 0, 1, 1, 0, 0, 1, 1, 0, 0 is correct. Cool. Now how do we mask everything with zeros? We need everything that is, to get zeros, we need to AND. To get zeros, we need to AND with all the non-zero values set to 1. Yes. We need to AND all the non-zero values and set them to 1. So 0 mask will have to be, all the X's will have to be set to 1's, and we do that instead. So, I've got too many nodes open. Node instances open. So this time, what do I want to do? Now I need all the X's set to 1's. And that seems to be the correct number. Okay, so that's good. So here when we add this value, right? I'm just going to set this in a couple of different ways. Let temp equals val. Temp needs to OR equals with 1's mask. and then temp needs to AND equals with 0 mask, then we write the value to memory. And we will do it with one number just to check that it's working. Ah, these need to be longs. Oh, that's kind of annoying. 36-bit. How do you work with longs in JavaScript? Does it matter? 36-bit unsigned. Big int. Is there, okay, we can take a look at that. Big int in JavaScript. Yeah, maybe we can big int these guys. See what happens. We need a 0b in front of it. Looks like. Oh, I need a $sign. My bad. We got temp before, we need more disk and ones mask. We want disk and 0 mask, just so that we have some numbers around here. Right, that seems correct, generally speaking. Wouldn't be too surprised if that was wrong. I guess we can test it. 131 in binary is that. So we have what? 1, 2, 3, 4, 5, 1, 1. So we would have 0, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 0, 0, 0, 0, 1, 0, 1, 1, 0. 0, 0, 0, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1, 0 is our final number. Yep, that seems correct. All right, I'm happy with that. Let's go. Cannot mix big int and other types. All right. So the question is, what is the sum of all values left in memory? Apparently it's this. We're going to give it a go, see what happens. Yes, we got it. Okay, cool, awesome. Ah, right, okay, I can use 0n for big int. That's pretty cool, actually, this big int thing. Neat, thanks for that tip, Blue Ghost. All right, second half. For some reason, the Seaports program still can't communicate with the Fairies docking program. Must be using version 2. Cool. Thanks for telling me now. Version 2 decoder chip doesn't modify values written in at all. Instead, it acts as a memory address decoder. Immediately before a value is written to memory, each bit in the bit mask modifies the corresponding bit in the destination memory address in the following way. If the bit mask is 0, the corresponding address bit is unchanged. If the bit mask is 1, the corresponding memory address is overwritten with 1. But if it's X, it is floating. A floating bit is not connected to anything. Instead, it fluctuates unpredictably. In practice, this means the floating bits will take on all possible values, potentially causing many memory addresses to be written at once. Consider the following program. When this memory goes to write to the memory address 42, it first applies the bit mask. Cool. So we get all the 1s in there. After applying bit mask, 4 bits are overwritten, 3 of which are different, and 2 of which are floating. Yeah. So we actually write to those. Next, the program is about to write to memory address 26 with a different bit mask. And this time there are 8 addresses that get written. Whoa. That's gonna be quite annoying to do. Well, we'll have to change these two functions we've got at the top because of that. Because that's not how these bit masks work anymore. I don't want to change these though, so I'm just gonna leave them like that. Paste it underneath, and we'll work on the second set. Okay, so right now, what are we doing? We still have the 1s mask, which is still all the 1s, right? All the 1s still get overwritten. Cool. But now we have the floating mask. This is like something for we want like generators or something, eh? We don't have to, but it would be interesting to do that. So the 1s mask, we still apply 1. We ignore the 0s don't matter, and the X's are the kind of sneaky things. I will probably there are different ways to do this. I think what I'll do is I'm gonna just keep track of all the positions that I X. Right? Like, so if I have a string that's 64 characters long, this is right to left, right? So position 63 is going to be bit 0, right? Okay, so let float bits is an array. Let's do that. Float bits equals new array. And then we're gonna do it this way. We're gonna say we're gonna start from let's just start from 0. I less than string.length, which is string is mask. I plus plus const. The index is going to be string.length -1 minus I believe. That seems to make sense. 63 becomes 0. 0 becomes 63. 1 will become 63 minus 1, which is 62, which is correct. Cool. And then we say if string index is an X, float bits dot push I. Cool, so that sets, or that tells us what all the floating bits are. And this is not how this works anymore, right? We need to check it. This is address is now the floating value. We still all the 1s mask, and then what we do is we say for each float b of float bits, we need to write a different. It's not even how it works. That's not how it works. No, we need to have every combination of all the float bits. Okay, so this is gonna be another. This is like so like a few days ago, maybe like 3 or 4 days ago, I did this like bit mask thing, and and I never explained it, I want to do something similar here. So what we need to do is we need to get every combination of all the floating bits, right? Because you can see here, if we have 2 floating bits, we end up having to write 4 different values. So if we have 3 different bits, we have to write 8 different values, right? Which is 2 to the power of whatever it is. Actually, before I do that, let me just... Oh, did I change the wrong ones? I changed the wrong ones. That's okay. Just mask that out. I mean, comment that out. So I just want to check that I'm getting the right results first. So this is bit 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, and then 35, 34, 33, 32. Cool. All right, so we're getting them all. So there are 8 here, right? There are 8 bits here, which means we actually have 64 different values to write to 2 to the power of 2. So how do I get that to the power of, how do I get all those iterations, all those combinations? One way to do it is I can, I know that there are 64 different combinations, right? And that's all the numbers. And the cool thing about binary is that if I list all the numbers from 0 to 2 to the power of the number of elements, in this case 2 to the power of 8, which is 64, no, 256, then that bit mask, let's say, right, gives me all those combinations. So the first one is when all those is everything is 0, and then when I is 1, that gives me just the first element of that array, and everything else is 0. So this is like a bit mask of the bit mask. Let me try and explain that a little bit better. The first time we go through this, I will be this. The second time I do this, I will be this, and then I will be these numbers, and so on, all the way until I get to I equals this, and then I equals this, right? So this gives me a way to really quickly select all of the bits in all the different combinations of these 8 numbers in the array, with each of them set to either 1 or 0. Let's see. So I can't. It's not. This isn't 8. First thing here. This isn't 8. This is. Let's call it n equals float bits dot length. So 2 to the n. So for each of these numbers, now I have a mask for the floating bits. Let float mask equals 0n, so a big int, address needs to be a big int. Oh, temp is the big int. Okay, cool. So temp now is what we're writing to, is going to have to equal value, and this happens in here at the end. But it's not going to be temp, because temp is the base. So we're going to have to call this base equals that or 1's mask, and we'll have to const that. So let's see, let temp equals base. We need to construct all of these numbers. Now we don't actually need to do 0, because if it's 0, then we're ORing with 0. So we can start from 1. That's okay. For each item in the float bits array, yes, for let j equals 0, j less than float bits dot length, which is n, j plus plus, if, and this is checking the bit mask, right? if 1 shifted by j and I, and with that I, with this and, bitwise and, we need to put brackets around it, or else, because the precedence otherwise automatically groups this way and you get really weird results, is 1. Okay, so what we're saying is if that bit is set, the first time this is run, that 1 bit shifted by j is going to be that the first time it's run in the loop. The second time it's looping, it's going to be this. The third time it loops, it's going to be this. The fourth time it loops, it's going to be this, and so on. So we're just checking every single bit in I to see if it's set. If it is set, then we need to set that bit to 1 in the temp address. Yes, temp and equals 1 bit shifted by the value in the float bits array. So float bits j. And then we write that. So we said that there are 8 values here, right? So the first time we run this, mem should theoretically have 256 values in it after the first write mem, if we did this correct. Or like something around there, because that value might already be 1. Actually, oh no, it has to be overwritten. Oh no, it has to be overwritten by what that value is. Oh, so we need like to build both the positive and the negative masks here. So I can't just do that. Because if it's 1, okay, if it's 1, we need to do that. And this is all equals, not and equals. That was a mistake. Else, if it is 0, right? Otherwise, if it's 0, we need to and equals, right? And this is where like bitwise stuff comes in handy. Not 1 bits. So these are like quite straightforward bitmask things if you've run across them before. So I used to do a little bit of low-level programming on my Nintendo DS, and so with that sort of stuff, you do bitmask stuff quite often with like hardware interactions. And I'm pretty sure these two do what I think they do. This one will always set this bit, whatever this value is. If this is 2, then this will always set bit 2 to 1. And this is, oh whoops, this is bitwise not, I think. I'm going to pretend it is. Is it bitwise not in... Yeah, I think it's bitwise not. I feel like it's bitwise not in JavaScript too. And so this will give me, how do I put this? This, if float bits j is 2, right, then this will give me a value with the second bit set. The bitwise not will flip it all around, so every other bit will be 1, and the second bit will be 0. Bit 2 will be 0. And then if I do an and onto the value, what that will do is that will unset the second bit. So I'm quite sure about that. And because of that, that means I actually get 256 separate values. And I should have, after one write mem, 256 different values set in my array. So I can console.log object dot, I guess, values mem.length should be cannot mix big ints with other types. So this needs to be a big int. Yep, and this also needs to be a big int. Can I do it this way around? So I have 2 values written, which is interesting. not what I expected at all. Let's see, what did I miss? What did I miss? Because flip bits here is 8 numbers in it, right? Yeah, 8 numbers in that. Yep, that seems legit. Flip bit slot length is going to be 8. That's legit. Did it loop that 256 times? It feels like it. I never used float mask. I'm only getting 2 different values out of this. And the 2 values I'm getting is flipping the second bit only. So I'm never flipping more than just the second bit. What's going on here? And that's not going to make a difference. Why am I only flipping the first value? Oh, of course it's not going to equal 1. Why would it equal 1? No, so we have to do this the other way around. So this is not greater than 1, this is greater than 0. This is not equals 1, it's greater than 0. So there are 2 ways to write this expression, right? There is the way I wrote it, which should be greater than 0, right? Because I'm shifting here, I'm shifting the 1 up. So I'm going to get 1, 2, 4, 8, 16, 32, and so on. So I need to check for greater than 0. If I want to check for equals 1, I have to do this the other way around, right? I have to go I bit shifted down by j and a 1, and then bitwise and that with 1. So these two checks are equivalent, and I mix the 2 together. So this is not by j, right? This is by, yes, by j. Yeah. And I guess it just depends which way around you like to think. But I mix the 2 together. I think more intuitively this way. So there's that. So that seems to be a lot of numbers now. It should be 256 numbers, which it is, which is great. Okay, so we don't want that anymore. We don't want that anymore. Cool. So, oh, cannot mix big int with other types again. The values aren't big ints. They don't have to be this time. So let's give that a go. If it's not, we can debug it. It's not! We can debug it. We will debug it. I'm quite disappointed in myself. I had so much hope for this as well. Maybe I should run it on one of these test inputs. So that should have, what, 12 values written? Yeah, well, if it's just 12 values, we can read it ourselves. It's gonna be 208, which it is. We have things written to 26, 27, 58, 59, and then they're overwritten by 16, 17, 18, 19, 24, 25, 26, 27. Okay. So it's either the fact that there are longs in here, like 36-bit numbers, that is messing up my, like, summing, or like, I don't think this is the issue. Whoops. Like, that should give me the same number that I tested with, yeah. Or my numbers aren't turning out right. Maybe it's my ones mask? I guess we can just test with some boundary conditions then. What if I set this to x, for example? What do I get here? Ah. That's not right. Set this to x. That's correct. If I set that, oops. I set that to x. That seems correct too. 35, 4, 3, 2. So setting this to x should still work. Oh, I got negative numbers in here now. But if I set this to x, I'm going to get some weird results. Yeah. Okay. Okay. The base is a big int. Ones mask is a big int. Is it? Oh, ones mask is not a big int. Oh, it is a big int. Well, like, it is eventually a big int. Maybe if I big int the 1 and then bit shift it. Maybe that will help. Oops. Wait. Why is it complaining about the second one and not the first one? Right, yeah. Okay, that seems more like it. So it was a thing, like, because JavaScript doesn't actually deal with integers, right? Like internally, like based on the spec, internally everything is a double. Like so engines like Node, like V8, like they all have optimizations to deal with ints and things like that. But once you go, it looks like once you go over 32, bits, like the size of an int, so it looks like JavaScript really needs you to use this big int stuff for anything over 32 bits. I wonder if that's true, because on the spec, when I checked it, right, it said, the spec that I checked earlier, it said if you need numbers greater than 2 to the 53 minus 1. But also doubles lose precision, right, after a certain point. So I wonder if that's what's happening here. So if I run this, I now should have a much bigger number than I had before. Yeah, okay, let's give this one a try, see what happens. There we go, we got it, okay. So if we use a different programming language, right, one that has explicit integer types, like Go or Java or something, then we wouldn't have run into this problem because we would have specified up front that we were using longs, which are 64-bit numbers, and everything would have been sweet. It's just that because JavaScript spec specifies that all numbers internally are conceptually doubles, we ran into this problem where certain, I guess, engine optimizations, maybe? I'm not gonna say that explicitly because I'm not sure exactly what's going on here. I don't have that detail. But based on these what we've just done today, it seems like, yeah, if you're gonna use integers greater than 32 on Node version 13 or lower, perhaps, make sure you're using big ints appropriately and everywhere, right? And so this was a bit of a catch, right? Like this is not enough because this is converting to a big int after we've already done this bit shift, right? Which means that internally this number has already wrapped around, or is non-existent. I think based on the results we had, this basically does nothing to the one. We had to make both of them independently big ints first, which then gives us an actual big int that is containing the value we want. So yeah, apart from that, cool question, cool problem. I liked it. You do need to. There are probably other ways to do this outer loop, but with bit masks especially, like knowing these two setups, OR equals to set bits according to a mask, and equals bitwise not to unset bits according to a mask. That's just a little bit of, I guess, trivia that some programmers who have come across that sort of stuff will know off the top of their head, and others will have to look up. But that is how you set and unset bits based on a mask in these sorts of programming languages. So cool. Thanks for joining me for today. I think, yeah, I think the second half I got like quite low this time. Like, oh no, 1.3K. That's okay. I wonder how many people are using JavaScript and are getting tripped up by these big hints. But yeah, thanks for joining me. And it was a cool question. I'll see you again tomorrow.